Okay, in question 5, we're again in the typical organic way, been given a formula, C4H4O4. We're told that compound B is a stereoisomer of compound A. And just to interrupt this, remembering that stereoisomers are actually divided into two groups: the geometrical isomers, which obviously have the double bond present, and optical isomers, which we have the different enantiomers capable of rotating plane polarized light in opposite directions. They both have different conditions for those. I sometimes make the mistake of talking about optical isomers in the term of that they're stereoisomers, but obviously realizing that optical isomers are a subgroup of stereoisomers. So there's two possibilities here. Back to the question anyway. So it's stereoisomer of compound A, and they've got a difference in boiling points, so that means obviously differences in the type of intermolecular bonding that goes on. It says compound A can form an intramolecular hydrogen bond. It reacts on heating with dilute sulfuric acid to form compound C. Now that reaction there should get you thinking about what's possible with sulfuric acid reacting. Now that could be an acid hydrolysis reaction, but we've got the same number of carbons, so also it's used in doing addition reactions of an OH and H across double bond. And we're told that compound C can exist as enantiomers, so that it's an optical isomer, so we're looking at having a chiral carbon in there. And then we're given some more information about compound A reacting with permanganate to form C4H6O6. So thinking about the reactions that permanganate can do, if it's got two H groups on there, or an OH group, is it going to be an oxidation reaction? If there's a double bond, is it going to be forming a diol? So you should be thinking about these different possibilities. Compound E is produced, which has a molecular formula. There's two of them, C2H2O3, and it reacts with tollens, obviously talking about an aldehyde group. And so, like a lot of these questions, there's a little bit of trial and error in getting started. So if we just start considering, sometimes it's best to work from the back, from say compound E backwards, or from some piece of information. In this case, with C4H4O4, there's only 4 carbons here, so maybe having a look at what compound A and B could be would be a good start. Now, with C4H4O4, we've only really got 2 possible carbon. Well, I suppose there's a fourth. We could have a complete carbon ring of some kind, something like this. It's a possibility, but these seem more likely A or B. So based on the variety of reactions that take place in this, my immediate thought would be to go with A. Now, obviously, if it ends up not being right, then you'd switch to one of the other structures. So just draw out some possibilities to start with. Now, my first thought would be to try one of these. I've put the double bond in the middle, and that's because we've got geometrical isomers here, and if we put it at the end, it wouldn't be possible to have a carbonyl group at the end, which seems logical with having 4 oxygens there. So for instance, if we were to do this structure, if we were to put the double bond here, we would just have a structure that just really wouldn't work. So the double bond going in the middle seems to make sense. It may not end up being the right thing, but obviously it seems also logical with having a geometrical isomer, that if we have 4 different, not 4 different groups, that would be an optical isomer, but if we have the ability to have cis and trans groups on either side, that would also work. Now, both of these structures actually have, seem to meet all the criteria as we go through. Now, initially when I first started working on this, this was a structure that I chose to start with, and I went through and there seemed like I thought there'd be a difference in boiling point here, but I struggled to contemplate it being that great a difference. And also the strength of the boiling point was quite high, and in one of the structures, and I didn't think that would suit having aldehyde groups there. Also, the other piece of information that came through was obviously the reaction with potassium permanganate. Now, if that happened, we'd get a reaction here and here, and we'd end up with 4 acid groups. That just immediately meant that this structure just wasn't the right one. So I can see where if you started this question you could go through for quite a way with this structure, and obviously not knowing all the physical data in terms of boiling point, but seeing that with cis and trans there may be a difference with either packing or the ability for it to form hydrogen bonds. Maybe there I can understand that. But as soon as we got to the fact that when this is oxidized, 4 acid groups, that didn't work at all. So that meant we had to go to this structure over here. Now again, this is a possibility that this may not work either, that we may need 3 carbons with you know, a double bond, something like, oops, I'll just change that. Well, something like this, where you had a 3 carbon chain. It may be possible after you've, you may work through the structure here and find this one doesn't work as well. So be prepared to do a bit of trial and error and seeing that they meet all the conditions, and don't give up on that. Okay, now just drawing out the 2 possible isomers of this. So really, this is a structure which we've got these 2 H's both going up, and that would make this obviously a cis, and this, the 2 H's going down, this would make this trans. Now they agree with the formula. There's 4 carbons, there's 4 oxygens, there's 4 hydrogens. We would see a reaction with sulfuric acid here across that double bond. Okay. Now obviously one of the things in this question is it is hard to go through and look at every single aspect, but just getting started on this, we can see where we could go with A, B, C, and then we're talking about a possible reaction of A to make D when compound D is it's reacts with potassium permanganate to form compound D. Now let's, having coming back to this, looking at these 2 and trying to sort out which one would be A and which one would be B. There's a difference in boiling point. It's assuming we've got the right structures here, which of course we may have to rethink, but at the moment we're going with it. So A is 135 and B is 287, so that's a huge difference, and we're told compound has ability to form an intramolecular hydrogen bond. Now just on looking at this by casual inspection, the cis structure seems to make sense with that. This is bringing the carboxylic acid groups close together so they have that ability to bond. The trans has them further apart, so they can't do that. So for instance, if we had the delta negative here, the delta positive here, delta negative here, delta positive here, and a delta negative here, and delta positive here, you could see where we could get an intramolecular hydrogen bond here. Now what that means is that this has less ability. Now for instance, this could now hydrogen bond with another molecule that's close to it. That's an intermolecular bond. This is within the molecule, this is an intramolecular bond. So even if you aren't sure of the how that bond's going to form in there, and this is my educated guess at what I think would happen, then it also has to be able to hydrogen bond with molecules. If this hydrogen bonds with another molecule, that's going to affect the boiling point. This one won't affect the boiling point in the middle here. Okay, that's just holding it together in a certain structure. This is its ability to bond with other molecules, and when these bonds are broken, that's changing its state, its physical state. So this one would only have one hydrogen bond that could happen. This one could have more than one. Okay, so that means we'd expect this one to have a higher boiling point, so that means that this must be B, and this must be A. So we'll go with that, and that's an explanation that you perhaps should give with justifying your choice. But of course, realizing that we may have to go back and alter this if this doesn't work out with the other reactions. Okay, so let's carry on at the moment. Looking at this, we have, all I've done is really redrawn compound A there, and just gone through what the question says. If you react it with dilute sulfuric acid, we form compound C, which has the possibility of enantiomers. Okay, and I've just drawn in that formula not very well, but C4H6O5. So we're thinking about if it's dilute sulfuric acid, that could be acid hydrolysis or something like that, but also it could be an acid-base reaction, but also it could be adding across this double bond here. So in potassium permanganate, we could be thinking about oxidation, but we could also be thinking, if there's a double bond, that we could be forming a diol across this as well, across the double bond over here. And then when obviously it is oxidized, so the fact that we've got an oxidation here would suggest that this isn't being oxidized in the way that we'd normally think of happening to an alcohol, or from an alcohol to an acid or something like that. And we get a positive Tollens test, so that really indicates that we've got a structure here which has only got 2 carbons, and that means we must have something like that, and with a aldehyde group, and that's used up 1, and that would kind of indicate that at the other end we've got this. Does that fit that? C23, yes. So that's an easy structure to get at the end. We know there's a carboxylic acid there. That's obviously not going to react through that, and that's the obvious structure at the end. So E is an easy one to get. So let's see if we can get some of the others. Now, I haven't done a very good job of it, but all I've done is draw in what I think would be an OH adding across this double bond, because obviously if we're going to have an aldehyde over here, which is very clear from the question, it's likely that if it's oxidized it comes from a OH group, and so that's what we've got on this side. Now obviously this is an unusual synthesis, and we just have to go with the information we think. When I say unusual, it's not the typical one you're taught in class or anything like this. We're told we're going to get an aldehyde. We've obviously had addition of OHs here to get that kind of reaction. It fits the formula, and so this must be the structure D. Okay, now we've got to work out structure C. And this structure is perhaps the most straightforward of all. Once, obviously, you've got to get A to get this, but when we look at this, we're just getting addition across the double bond. Just make sure when you do these addition reactions, or the reaction with the the 2H groups down here, that you actually do get rid of the double bond and don't leave it in there accidentally. Now, with C, obviously, we've got the information that this has got to be an enantiomer. So I'm just checking on that. So we need 4 different groups. So if we were to look at this carbon here, for instance, and in the question, obviously, if it suggests this, you've got to show it. So, that would be a chiral carbon. We've got 1 group there, 2nd group here, 3rd group there, 4th group there, that are all different. So that's A to E, and but we've also got to do some reactions now. Okay, now in this final part, for this part, is balancing the equation. Now we're going from this organic molecule, which has got a aldehyde and carboxylic acid, and we're going to one which has got 2 carboxylic acid groups. Now if we just write that out as a normal redox reaction, to balance that, we'll notice that we've got 3 oxygens on this side, we've got 4 on that side, so we add a water to get 4 oxygens on both. That immediately means we've got to balance the hydrogens. We've got 4 on this side, so we add 2 H pluses. Now, Tollens is done in basic conditions, so if you didn't know that, that could end up causing some problems. So to balance that, we add 2 H minuses there, 2 H minuses there. obviously that's going to mean that's going to end up having two waters here. One water there, that's going to cancel, and that's going to leave two H minuses on that side. Now to balance that, we need to put plus 2 electrons on that side. Obviously with Tollens, kind of the silver mirror test that we're talking about, we're going from silver, a silver ion, to a solid silver, and that would be obviously plus an electron there, and because that's got 2, we've got to times that by 2, and then it would just be a matter of combining those two equations to get it together. So we'd have 2 Ag plus COOH CHO goes to COOH COOH, and I missed out the plus 2H minuses there, and plus 2 silver on that side, and plus, that, even though that cancelled there, that cancelled to make one water, okay, because there was just one there, so plus H2O. So take care with your balancing and cancelling there, and that's that one.